In this video, we'll be looking at the design steps for singly reinforced beams using limit state design. So in the limit state design, we have four type of problems. First one is finding depth of neutral axis. Second is finding ultimate moment of resistance. Third is finding area of tensile reinforcement. And fourth one is design of section for given ultimate moment or ultimate load. In the design, we would be finding what is the effective depth. Then from that we need to find out what is the area of tensile reinforcement required, all this. So in the first type of problem, we'll be finding the depth of neutral axis if all the sectional dimensions are given. So the equation is xu equals to 0.87 fi ast over 0.362 fckb. So the same equation can be find out in clause G 1.1 page number 96 of IS 456. So if the AST is given, if the width is given, then it is very easy to find out the depth of neutral axis XU. In addition to this, we would be differentiating what type of section for a given dimensions we will be getting. So these are the XU max by D, that is limiting a depth of neutral axis in terms of ratio with respect to effective depth. They have given in the clause 38.1 page number 70 of IS 456 2000. So for 250 grade of concrete steel it is 0.53, for 415 grade of steel it is 0.48, and for 500 it is 0.46. If we want the what is the XU max, that is limiting depth of neutral axis, we just want to multiply these values with the effective depth D, then we'll be getting XU max. When we compare this XU with XU max, we can differentiate. If XU is less than XU max, this is considered as a under reinforced section. If XU is equals to XU max, then it is considered as a balanced section, and if XU is greater than XU max, then it is a over reinforced section. So the second type of problem is finding the ultimate moment of resistance. So the ultimate term is used when we would like to find out the moment of resistance of a given section using the limit state design. If we want to find out the moment of resistance as per the working stress method, then instead of ultimate we'll be getting allowable moment of resistance. So that is the terminology which differentiates the design philosophy which we need to use it. So for finding the ultimate moment of resistance, there are different steps. The first step is to find the XU, right? That is depth of neutral axis. So in the question they will be giving what is AST, number of bars, and what is the width, and what is the effective depth as well. From this we need to find out what is the depth of neutral axis. Then we need to differentiate the type of section as was discussed in the previous type of problem. Then we need to find the moment of resistance. So this moment of resistance, if the value of XU over D is less than the limiting value, then the moment of resistance is calculated by following equation. So this equation is given in clause G 1.1 page number 96 along with the same statement. This indicates that if XU whatever we have got here, if it is lesser than the XU max, then we will be using this equation to calculate ultimate moment of resistance mu. If the value of XU over D is equal to the limiting value, the moment of resistance of the section is given by the following equation. So this is the equation. So this is given in the same G 1.1 page number 96. So here we'll be using XU max over D. When it is a balanced section or over reinforced section, we'll be using this equation here. So the third type is to find the area of tensile reinforcement when the factored moment is given. They will be giving the factored moment, the width and the depth as well. We need to find out what is the area of tensile reinforcement. So before that, we need to find out what type of beam or section they have given. So we can find out the mu limit. So mu limit equation is the same equation which we discussed. This equation given in clause G 1.1, page number 96. If you substitute all this, we'll be getting what is the mu limiting moment of resistance. If the moment whatever they have factored moment whatever they have given, if it is less than this, then that is under reinforced section. If it is equal to this, then that is a balanced section. If it is greater than mu limit, that is over reinforced section. If mu is given, if mu is less than mu limit, then this is the equation we need to use to find out the area of tensile reinforcement. If mu is greater than mu limit, then we need to design the beam as a doubly reinforced section or increase the depth of the given section or redesign with the increased depth. This is the third type of problem. And in addition to this, we need to find out what are the number of bars required. So in the fourth type of problem, we'll be designing the section for a given ultimate moment or ultimate load. So in this we will be they will be giving us the width of the beam, or we need to assume the width as well. They will be giving at either the ultimate load or ultimate moment. So in the step 1, we need to find out what will be the depth. So to calculate the depth, we will be assuming that the section is balanced. So the equation is here is d is equals to square root of mu over ru limit fck b, where ru limit is nothing but 0.36 k into 1 minus 0.42 k, where k is nothing but xu max over d, which this coefficient can be obtained from the similar to what we have discussed in previous xu max over d for different grade of steel. So once we found out the effective depth, this will be we need to increase the effective depth by 5 to 10% based on the depth which we have obtained. If the depth is lying below 500, then we will be assuming 5% increase, or if it is greater than 500 till 1000, we need to increase it to the 10%. And in addition to that, we need to round it up to the nearest 25 mm. Once we have found out the effective depth, rounded effective depth, then we need to find out what is my overall depth. Overall depth is given as small d, that is the effective depth, plus cover from the IS code we need to find out based on the exposure conditions, and then the assumed diameter over 2. This will give me the overall depth. In the step 2, we will be finding out what is the limiting moment of resistance, and we need to compare it with the given ultimate moment or calculated ultimate moment. This is required to distinguish what type of beam or section we are designing. So if mu is less than mu limit, the mu limit is given in the IS code as well, that is clause G 1.1, page number 96. Then the beam is considered as under reinforced section. If it is greater than that, then we need to redesign with increased depth. So if we are using this equation, we'll be getting the how much minimum depth is required for the given moment. So most probably this, if after calculating the depth and increasing from 5 to 10%, this condition will be satisfied and the beam will be designed as an under reinforced section. Once we have distinguished and compared with the mu limit, the third step is to find out the area of steel. So area of steel required can be calculated using this equation, and the next step is to find out the number of bars. The number of bars can be obtained by dividing the AST required with the assumed number of diameter of bar, area of the assumed diameter of the bar. With this we will be getting some decimal point, and we need to round it up to the nearest to 0 value. And once we have found out the in terms of like normal value, then we'll find out what is the AST provided. That is nothing but the round off value into area of the bar diameter which we have shown. While after calculating, we need to make sure that AST provided, that is the calculated value, should be greater than or equal to AST required. So obviously if the rounding off is the nearest to 0.0, then definitely this area provided will be greater than area required. And in addition to that, we need to perform the checks. So as per clause 26.5.1.1a, page number 47 of IS 456, the minimum area of tensile reinforcement should be calculated using this value. So AS over BD equals to 0.85 over Fy, where BD, if we send on that side, we'll be getting, we already know what is my width, what is the effective depth, and Fy will be getting some value. Okay, this value, this is the minimum reinforcement we need to provide, and the what is area AST provided should be greater than this value. If it is lesser than this value, then we need to provide this much tensile reinforcement. And the last step is we need to find out what is the maximum tensile reinforcement. This is also given in the clause 26.5.1.1b, page number 47, that is 0.04 into B capital D. So this is the maximum tensile reinforcement needs to be provided for the given section. And we need to make sure whatever AST provided should be greater than or equal to AST minimum, that is minimum tensile reinforcement, and whatever AST provided should be less than or equal to the maximum tensile reinforcement given. With this, the whole design problem will be complete. With this, I am ending this lecture. Thank you.